Okay, welcome back. In the first video we have seen the basic structure of Fourier transforms, and of course one important thing is that the Fourier transforms always appear in pairs. The Fourier transform and its inverse Fourier transform and its inverse transform, usually they are pairs, they have some connection. Inverse Fourier transform, so if you use the equation, say you are transforming f of t, you are taking the Fourier transform of f of t, and you will get a function in omega. So that, of course, that is equal to 1 by root 2 pi integral minus infinity to infinity, then our function f of t into e raised to minus I omega t dt. Now if we use this equation, if we select this equation as the Fourier transform, then of course its inverse Fourier transform should be related to that. So its inverse Fourier transform. So the equation for this inverse Fourier transform, what does inverse Fourier transform mean is that if you know the Fourier transform, you can recreate your original function. You can trace back your original function f of t is equal to. So you take the inverse Fourier transform of your transform. So you will get your function, the original function you will get, that of course that is equal to 1 by root 2 pi integral minus infinity to infinity. Here we have what is known, what we have in our hand is f of omega multiplied by exponential plus I. That is very important. If you use minus I in the Fourier transform, then in the inverse Fourier transform you need to use plus I then omega t. There is no change in that variables, and multiplied by d omega. So these are the Fourier transform pairs, and imagine someone used in the Fourier transform, someone used e raised to I omega t. Of course there is nothing wrong in doing that, but if you use e raised to I omega t in the Fourier transform, you need to use e raised to minus I omega t in the inverse Fourier transform. That's very important. So these pairs are always, they have some connection. Wow, the exponential is just what is opposite to what you have used in the other case. So these are the Fourier transform pairs. Both of them are usually known as Fourier transform pairs in mathematical, of course not as mathematical physics, in almost in mathematics they are known as Fourier transform pairs. And if we use the function in space, I will show you that if we have that function in space and you are taking the Fourier transform of that function in space coordinates f of x, and I already told you you will get a function in momentum space. This is equal to 1 by root 2 pi integral minus infinity to infinity the function f of x, our original function, multiplied by e raised to minus I kx dx. And if you use this particular equation for finding the Fourier transform of that function, then definitely the inverse Fourier transform of f of k and you will get your original function by taking the inverse Fourier transform. And the structure is, there is no change in that constant, there is no change in the limits of the integral. Now here it's f of k, because we know f of k only, we are going to find f of x, multiplied by exponential. You see, in the first equation we use minus I, here you need to use plus I. That's very important. So bk. So this is the another pair, Fourier transform pair in position and momentum coordinates, Fourier transform pairs. Okay, thank you very much. In the next videos we will be dealing with some important problems related to Fourier transforms.